Closing keynote. Thank you all for coming. It's wonderful to see you all here. I've had a chance to talk to a few of you, not everyone, but there's still time. We have a little reception afterwards. But thanks for coming. Apache Druid 31 is out, big news. I hope to be the first to tell you that. That's a few hours ago. And the timing's good because I'll talk about some of the stuff that's new there and also what's coming next. So let's talk about what's coming next for Druid, how to tie together some of the things we talked about today. So I want to call back to this picture here. This is a picture you saw in Eric's talk that opened up the day. And I think he talked about things from a conceptual level, and I'm going to bring what's our roadmap into this picture. So the event query engine, you know, as Eric mentioned, we think of Druid as being the ideal query engine for the event-oriented system, the ideal query engine for events. And what does that mean? What are the parts of building a query engine? So when I think about the Druid roadmap, when I think about where we're going, I think about we need to evolve the different parts of Druid to meet evolving use cases. And so every feature we think about fit into this sort of paradigm. So at the bottom layer, you have the storage layer. That's object persistence, caching, indexing, push down of filters. That provides the query engine with data. You have resource management. That's deciding what queries to run, their priorities, memory allocation. You have the local query engine. That's server local, each individual server. That provides us with vertical scalability. And then you have distributed query engine, which works together with the local one that provides horizontal scalability. So these are all the pieces, and they're all important to build a good event query engine, and we think about evolving each one of them as part of the roadmap. Some of the projects, I'm going to highlight 3 projects that we have planned for the coming year, so the next 3 or 4 releases of Druid. The first one, embedded projections. That's easy to maintain, materialized views. Dart, which you heard about earlier from Will's demo, which is experimental in Druid 31 today, and we intend to be bringing it to GA in the coming releases. And a virtual storage layer that is not available yet, not actually being worked on yet, but is on the drawing board right now, and I want to talk about where we want to go with that. Many more things will happen, but these are the 3 I'm going to talk about. So first off, embedded projections. Embedded projections is really something that affects, it lives in the local query layer and the storage layer. A lot of distributed databases do their projections or materialized views or what have you at the distributed query layer, where the SQL planner determines whether to use a view or not. We're not going to do that. We're not doing that because it makes it very difficult to manage the creation and evolution of materialized views. So imagine when you create a new one, it may not be fully populated yet. You have a data set that has billions of rows. It's going to get populated over time. While it's being populated, you want to be able to use the materialized view for the data where it's populated, and you use the base data for where the view is not available. To make that possible, we tie it into the local layer, so there's a local decision about where it's going to whether to use it or not. And that's this picture. So embedded projections is actually a version of it shipped in 31. There's a note in the release notes. There is a bug with it that makes it not super usable in production. But those of you that are intrepid into the code base, like the code is like all there, and that bug will be fixed soon. So you can check it out in the code base, and there'll be a nice like more usable version in 32. So anyway, there's local decision at the historical node, routing between are we using the base data available in the segment or an embedded projection that's in the segment. So what we're doing is the same segment files on deep storage are going to have the base data in them, and they're also going to have various projections, 0, 1, 2 projections. We think most people will use either none or 1 or 2. And in the first version, what we have available for projections is rollups. And so you may have 1 or 2 extra rollups defined in the segment that the historical will use if it's available. Is this legible? Sort of. It's sort of legible. So here's an example of how we might lay data out within a segment. So in the big table here, you have the base data. So lots of columns, lots of rows. And what you have in this dotted line on the bottom is you have a projection. So this is a segment with 1 projection. And you can see the projection has fewer rows and fewer columns. And so the fewer columns is you define the projection by which columns you want to include. And because we are doing a aggregation, we're doing a pre-aggregation in that projection, you have a smaller number of rows that is going to scale with sort of how complex those columns are that you've included. So the use case for this is, for example, let's say that you have your base data is at a time grain of a second, but maybe lots of your queries are looking at hourly data or maybe not even looking at time grain at all. You might have a projection that projects it out to hour. So it might store a second version and an hour version. Doesn't have to be time. It could also be any other dimension. So you can kind of do various things with this. Benchmarks are like a little bit silly to do with projections because they could be as fast as you want them to be. I mean, you can design a benchmark for projections where you're doing a aggregation of a single column and you make a projection that only has that column and it takes like 1 millisecond for like 10 billion rows. So you can kind of make them whatever you want. So we did this, we made them this. This is sort of a realistic benchmark, we thought, a scenario that might actually happen in real life where you're not going all the way down to one row for a projection, but you're sort of dropping some high cardinality columns. So I think this is what a reasonable real world expectation is. For queries that match the projection, they might speed up by like 2 to 10x. Dart, this is available in Druid 31, experimental. Take a look, we'd love your feedback. Dart is something that is really involved with these top 3 layers, doesn't touch the storage layer at all, which I could see a little faded pink here, but you can't see it there. It doesn't touch the storage layer at all, but it does touch the resource management, local query, and distributed query layers. Dart is part of a movement that we're making towards having multiple engine profiles in Druid. So as you heard earlier, Druid originally had its native query engine that's designed for real-time analytics applications. That's why Druid was created in the first place. A couple years ago, we introduced the query task engine that's intended for batch jobs, ETL and ELT, loading data, replacing data, bulk operations. So we had those 2 extremes, and then Dart sits somewhere in the middle. So in terms of parallelism, it's fully parallel like query tasks. In terms of latency, we're targeting lower latency queries. The query tasks are targeting higher latency because they run in tasks, they run in their own JVMs. A query task, even if it's processing just 1 row, is going to take a few seconds to run minimum, whereas a Dart query can run in milliseconds or less. Targeting high concurrency, just like the native engine, and having server level elasticity, just like the native engine. So you add and remove servers that are relatively persistent. Query tasks you can run directly in Kubernetes, and so you don't really add and remove servers for query tasks. You can kind of auto scale on the level of an individual query. So it's in an interesting place in the system because it's actually the same engine as the query tasks. So query tasks and Dart are the exact same engine with a different what we call a profile. And a profile controls things like what kind of fan-in are we going to use? Are we going to fan into a single server? Or are we going to fan to multiple servers? What kind of shuffle are we going to do? Are we going to have fault tolerance or not? Are we going to use durable storage for checkpointing, or are we going to do things in memory? So these kinds of decisions can go one way or the other, but at the end of the day, they're in the same engine being configured in 2 different ways. One for high latency, highly elastic use cases, and one for low latency, less elastic use cases. There's another interesting question, which is Dart and native. So Dart and native they're different engines. They have the same storage layer. They run on the same servers. And so there's like a little bit of a fuzzy dividing line between them. It's like, when would you use Dart? When would you use native? Well, the answer today is Dart is experimental. So you're going to use native in production, and you're going to use Dart when you're screwing around. But where are we going with this? And where I'd like to go with this is I'd like to have one engine with multiple profiles that handle a variety of workloads. And so you think the query tasks are a profile of the multi-stage query engine that is designed to launch on Kubernetes and be super elastic and be fault tolerant and all that stuff and run for hour-long batch jobs. And Dart for the other 2 things. Dart for real-time analytics apps and also for data warehousing style queries. There is a little bit of a fuzzy line between those, and I think it makes sense to handle those with the same engine that is capable of handling both of those. Maybe one difference might be that you'll configure for preloaded data for real-time analytics apps, and you might have data fetched on demand and cached from object storage for your more business intelligence workloads, which I will talk more about that later when we talk about virtual storage. So I want to compare Dart and native a little bit to give you an idea for, you saw in a demo earlier, a complex query that Dart handled many times faster than native, and like why does it do that? It's mostly about being fully parallelized through each stage of processing. So native here on the left has fully parallel leaf processing, and then single-threaded post-leaf processing. Single-threaded, I should have a star there, because there's actually some cases where it can be like lightly multi-threaded. But most of the processing, for the most part, after the leaf is single-threaded. And so this creates things like, we call it the broker bottleneck. So if you have a subquery, the broker collects all the results of the subquery on the broker, and then does further processing on the broker, generally in a single thread. And that means if you're joining two big subqueries, like that join will be, the subqueries will be collected on the broker, the join will happen on the broker, and so like it can take some time, it's progressing one thread at a time. In Dart, every stage can be fully processed, so every stage runs the same. There's nothing special about the leaf stage. So rather than just the leaf stage being fully parallel, like every stage can be fully parallel. Brokers do not participate in processing, so it's a bit easier to think about how to scale the system. There's only one kind of server processing data you can just add more of instead of having to think about, do I need more brokers or do I need more data servers? And the model is actually a generalization of the native model. We can still set parallelism for non-leaf stages to 1, and if you do that, then you get an execution tree with Dart that looks the same as the execution tree with native. If that's something that you want for your workload, then you can do that. In terms of benchmarks, so I did some benchmarking, so I want to show you where things are now in Druid 31. So first off, here's a needle haystack test. So this is a test on the New York City taxi data set. This is a query that returns 2 rows. So it's the result of this is 2. It's a count star. So it's a needle in a haystack. We're hitting a specific filter, and because we're using indexes, it's like a very fast query. So we can do it in 6 or 7 milliseconds. This is numbers from my laptop. Native was able to push a bit above 1500 QPS, and Dart about half that. And there's various reasons. I think that this is a good start. It's showing that the priority certainly when building Dart was about being able to handle those data warehousing and business intelligence workloads. So it's, I think, promising that even though it was not really a goal to handle high concurrency workloads, like we're doing all right, even though we weren't even really trying to do very good at this. So I think if we try to be good at this, then this gap closes. In terms of what we were trying to do with Dart, what we're trying to do is be better at more complex SQL queries, more BI sort of workloads. And at that, we have a suite of test queries that we tested that are all on the bottom, ordered from biggest to lowest speed up. So many of the queries, more than half the ones we tested, and these are all queries that are sort of large, complex SQL queries with lots of subqueries and high cardinality group bys and exact count distinct and the kinds of things the native engine is not good at. So it's kind of a benchmark that's to some degree stacked against the native engine. Anyway, more than half the queries, Dart being faster. This was testing done on a 64-core EC2 instance, and in some cases, 2,000% faster. There's some queries where they're about the same speed, and then there's some simple queries. This benchmark wasn't all heavyweight ones. There's some simple queries that are lightweight where native is faster. I think what I see from the benchmarking is we're doing pretty good out the gate with this engine for lightweight queries and pretty good for high concurrency. Not as good as native, but decent. And we're doing very well for the kinds of heavyweight, complex queries that we built the engine for in the first place. So I'm excited about the possibilities. The last thing I want to talk about, virtual storage. So virtual storage, you notice that Dart covered the top 3 boxes, and virtual storage is the last one, so they actually can work together to build a complete story. Virtual storage is a system we're building where the goal is to unify cloud storage, local disks, and memory into transparent storage for historical data. This is for the historical system. Real time uses a whole different storage engine. But for historical data, to unify things in this way. So you have in deep storage, loading 1 column at a time is the vision. into local storage. Today, we load an entire segment at a time, so we'd like to granularize that to one column at a time. In local storage today, we have a preloaded cache based on load rules for the native engine and for Dart. And we have on-demand, not a cache, but just on-demand pull one segment and throw it out for query tasks with no caching. So imagine query tasks and the interactive engines all running on top of this system that is able to both have some preloaded stuff based on load rules for persistent servers, and then also have some cache that's populated as well for, imagine you say my older data, I don't want to pre-populate it on the servers, I just want it to be loaded on demand. And then one page at a time from that goes into local memory. This is how Druid's always worked since day one. It's always loaded one page at a time from local storage. That's not changing into page cache. And then the query engine reads from that. So really the evolution here is all happening. The action is all kind of in the deep storage to local storage area. The stuff to the right of that is we're happy with it and it's not changing. So the idea here is, on the query engine, the storage layer, we have a variety of query engines. The native engine, we have 2 profiles of the multi-stage engine. Query tasks for batch jobs, native or Dart for interactive queries, and then all queries running on the same storage layer. So the idea is that you shouldn't have, you don't want to have like a different storage layer for each query engine. That's like a little bit too crazy. So all query engines running the same storage layer. And the storage layer has 3 pieces to it in where we're going. One is historical, like I mentioned, that's cloud-based with local disks and in-memory caching. There's real-time storage. That's temporary storage in real-time tasks before persisting in deep storage. So that's a special kind of storage that's used just for the most recent, generally 1 hour of data that's in the real-time system. And then external. So we talked earlier in the day about integrating Druid with Iceberg and Delta Lake, the lake houses. I think there's a lot of interesting things we can do there with, we're able to query Parquet files in Druid using query tasks today. We cannot query those files with the native engine or with Dart, but I think it would make total sense to be able to query them. It would make total sense to be able to cache them locally. And so I think that kind of stuff is made possible by, by kind of like splitting the layers in this way and then plugging the query engines on top of the layers. So, imagine caching the Parquet files locally, and imagine even the interactive query engines being able to run on Parquet files. I don't think you're going to be getting 1600 QPS on a laptop on Parquet files. That does rely on the indexing that we have in Druid. But it'll work and it'll be like reasonable for an external table, I think. But yeah, so we have a lot of cool stuff coming. And I hope that you try out Dart and Druid 31. Let us know what you think. If you're interested in checking out the code of projections, check that out. And then keep an eye out for a fully functional version in a future release. And then stay tuned for virtual storage and see how it all fits together. And thanks, everybody.